So this is number 45 in the homework on what page is it?
Page 322.
Page 322. Y equals, was it 1 over x plus the natural log of x?
Yes.
1 over x log of x. So, domain. That's the first question we ask. What's its domain? What x values are you allowed to plug into the first term? Everything except for 0. The second term, however, log, that's much more restrictive. It doesn't like anything unless it's positive. So that includes 0. It only wants positives, not 0, not negative. So what's the domain? X has to be greater than 0. Or everything from parenthesis 0 to infinity. You could say it either way, right? Okay? That's our domain. All right, next on the list of things to check for, let me go down that checklist again. Getting it in the right order here. What do they have up next? Intercepts. Intercepts are next on their list. So finding the intercepts means finding out where x is 0 or y is 0. Now what do we already know about x being 0? You can't do it, so we can't even look for that. We could look for where y is 0. Okay, so let's see if we can find anything there. Y is 0 would lead us to an x-intercept if there is one. Okay, so we would have 1 over x plus the natural log of x equals 0. But then we get kind of stuck. We don't really know how to solve that kind of an equation. It's a mixture of algebra, 1 over x, and this transcendental function, log x. It would mean you're looking for where is log x equal to negative 1 over x? I have no idea. About the only way I could solve that is with a calculator. It may not even have a solution, but if it has one, I can't find it using algebra. There's no algebraic stuff you can do there. I mean, you could take the exponential of both sides to get rid of the log, but that just makes the other side worse. You'd get x equals e to the power of negative 1 over x. It's just about as bad as we had to start with. You go round and round in circles. So this is one of those times I just give up. There's no algebra, there's no math you can do to solve that. You can't get the x-intercept, even if there is one, using algebra. You could with a calculator. How would you do this with a calculator? Well, you just plug it in, turn on the plot, trace until you hit 0. There's even in the math menu, there's a 0 command. It says find the zeros of this function, and you can tell it to find it for you, and you get some decimal to do it. But there's no way to do it on paper. So let's skip over the intercepts. We're not going to be doing any intercepts today. That moves us on to symmetry next. Now, symmetry is kind of off the table. The log takes care of that, doesn't it? Because what's the check for symmetry? You plug in a negative x in place of the x? You can't plug a negative x inside a log, right? So no symmetry. Symmetry's off the table as well. So move on. Boy, we're burning through these fast when you get to skip them. Next up is asymptotes. Well, we're definitely going to get an asymptote. There's obviously a vertical asymptote where? At 0. Yeah, because that triggers division by 0. So there's a vertical asymptote there. Okay. So vertical asymptote is going to happen when x is 0. Now, we know that x cannot literally be 0. We've already said it's outside of the domain. But what we're implying here is that as we come in towards that, we're going to be heading off towards some sort of infinity. It's a little debatable which infinity, because the two terms in a way are kind of fighting against each other here. What does the log graph look like? Log graph looks like this, right? What does 1 over x look like? 1 over x looks like this. And we're adding these two together. Now, we lose this part because it's not in our domain. We're adding these two together. And they have opposite infinities in mind, don't they? When you add them together. The log is heading to negative infinity, and the 1 over x is heading to positive infinity. As you come in towards 0 from the right side, they kind of have different destinations in mind. So to actually find out where it's going, what would you have to do? you'd have to take its limit towards 0 and probably end up doing some sort of analysis using L'Hopital's rule or something like that. Okay? So let's find out what happens. What is the limit as x approaches 0 from the right side of 1 over x plus the natural log of x? Well, as we've already said, what does this first term head towards? As you head towards 0, it heads towards infinity. Whereas where does the log head towards? Negative infinity, right? And that's an indeterminate form, like we talked about in that section on L'Hopital's rule. So this was the trickiest one. We did not have a universal trick that worked on all of these. We said you had to kind of think of them on a case-by-case basis. But if you had two terms, oftentimes, if fractions were involved, what might help? A common denominator, we said. Sometimes getting a common denominator can help. What is the LCD of these two terms? X, yeah. So I'm going to rewrite this with an LCD. All over x. Up in the numerator, you'd have 1 plus x natural log of x, like that. Okay? Now as you head towards 0, it's even more complicated, because the bottom's heading for 0, but what's the top heading for? That 1, all right, fine, but what about this part? Where's that heading towards? Isn't that another indeterminate form that's shown up there? Because this guy in front's going to head for 0, but the log is going to head towards negative infinity. So right there, you've got an embedded other problem. You don't even know where that's going. Okay? That is heading on its own towards 0 times negative infinity. And this guy is heading towards 0. So I don't even know yet whether I can use L'Hopital's rule on that or not. L'Hopital requires what to happen? 0 over 0, or infinity over infinity. I need this to go to where in order to use L'Hopital's rule? No, overall I need it to go to 0, so I need this term to go towards negative 1. So now I'd have to go take the stuff I've bracketed in red there and do it as a separate problem, hoping it's going to go for where? Negative 1, so that I get to use L'Hopital's rule, because if that's not allowed, I don't know what I'm going to do. All right, so put this one on hold for a moment. Okay, it's on hold, we're not done with it. We need to focus on this little subpart here, see what it's doing. Is the limit as x approaches 0 from the right of x times the natural log of x. I think we actually did this one in class as an example. I may be misremembering though. As we said, it goes to 0 times negative infinity. And we know a trick for that. How do you handle that combo?
Move one to the bottom.
Yeah, move one to the bottom. Probably the x would be the easier choice. Move it to the bottom. And we get the limit as x heads towards 0 from the right of natural log of x divided by x to the negative 1. Okay, now that is now going to go towards negative infinity over positive infinity. I know because I've got the graph of x to the negative 1 right here. I can see it's going to plus infinity. So this is going to plus infinity because that's this. So I can use L'Hopital. Apply L'Hopital's rule, and I get the limit as x heads towards 0 from the right of the derivative of log x, which is 1 over x, divided by the derivative of x to the negative 1, which is negative x to the negative 2. Rewrite that. That's the limit as x heads towards 0 from the right of 1 over x over negative 1 over x squared. I can invert and multiply because I'm taking a fraction divided by another, and I get the limit as x heads towards 0 from the right of 1 over x times negative x squared. That reduces to negative x. The limit as x heads towards 0 from the right of negative x, which would be 0. Okay, so that heads towards 0. Not what we were hoping for. We were saying we wanted L'Hopital's rule to work. Doesn't appear that L'Hopital's rule applies here. So, we can take this back off hold. We can now say where it's heading. We know what the guy in the red box is doing. He's heading for 0. That's what all this work was about. Okay, so we're taking that back off hold, and we have that that is equal to the limit as x heads towards 0 to the right, from the right of 1 plus x, natural log of x, over x. And we now know that this piece here is heading towards 0, and this piece is heading towards 0 as well. But that doesn't account for the 1. So what's the numerator heading for overall? 1. Whereas the denominator is heading towards 0 from the right. Now if you divide 1 by something that's getting tinier and tinier, but staying positive, where are you going? Infinity. It's a long way getting there, but we got it in the end. When you add these two asymptotes together, the log asymptote and the 1 over x asymptote, it would appear the 1 over x asymptote wins that. Because when you add them, what do you get? Plus infinity. That's this guy winning, isn't it? He's saying, no, we're going to plus infinity. He's saying, no, we're going to minus infinity. This guy wins. We're going to plus infinity. There's an asymptote there that goes up. So we have a vertical asymptote that goes up as we come in towards it at 0. Boy, that was a lot of work. Now we get at last into the calculus stuff. So we start taking derivatives, y prime, y double prime, all that stuff. So y prime, the derivative of the original function. Think of that 1 over x as x to the minus 1. What's its derivative? Negative x to the negative 2. And log x's derivative is 1 over x. So there's our derivative. Might be useful to write it as a fraction for the purposes of seeing where it's 0. So I could write this as negative 1 over x squared plus 1 over x. LCD would get me x squared on the bottom, negative 1 plus x on top, or y prime is x minus 1 over x squared. That's probably the prettiest form we could write it in. There's our first derivative. Okay? Now, let's look for the critical values. Critical values are where the derivative is what? 0. Okay? Fractions are only 0 where the numerator is 0. So that means x minus 1 is 0, which means that x is 1. We have a critical value at 1. There's also the possibility of a critical value because it's a fraction of where you divide by 0, right? Undefined. Where does that happen? 0, but that is not in our domain, so we throw it away. Okay? The other kind of critical value, y prime is undefined. There is such a place at x equals 0, but we throw it out. It's not in the domain. Remember, our domain starts at 0 but does not include it. So toss that one on. We only have one critical value worth looking at, 1. We now do our test. 1. I'm going to mark 0 here with a dotted line, and I'm going to cross-hatch this part out because why? I can't go back there. That's out of my domain. I'm not even allowed over there. Okay? Dotted line is telling me there's an asymptote there at 0. So check on both sides of 0. Remember, we're checking y prime. And here's its formula. Really easy to check because the bottom is always positive. So if I put something less than 0, like 1/2 in, 1/2 minus 1 is negative. So it's negative there. But if I put something like 5 in, that's positive. So it's positive there. So it's decreasing on the left and increasing on the right, meaning that at 1 we have what? A local min. Okay. Any questions so far? All right, second derivative stuff. Our first derivative, I'm not going to use this version of it for the derivative. I'm going to use that version. In fact, I'm even going to rewrite this as x to the negative 1. So this is negative x to the negative 2 minus, plus x to the negative 1. So y double prime would be 2x to the negative 3 minus x to the negative 2. Y double prime is 2 over x cubed minus 1 over x squared. The LCD would be x cubed. So y double prime is 2 minus x over x cubed. Is that right? Okay with that? So there's the derivative, the second derivative. Now look for the hypercritical values. Hypercritical values are the places where it is either 0 or undefined. So where is the second derivative 0? Where the numerator is 0, which is where? 2, yes. The other kind of critical value, same story as last time. That would happen. It would happen when the denominator is 0, which would be when x is 0. But what do we say about that? Again, not in the domain. Okay, that's not in domain. So we do our test for the second derivative now. This is y double prime now. 0, asymptote there, crosshatch back here, not allowed there. 2 is the place we're checking. It's the one and only hypercritical value that's worth looking at. Check both sides of 2 in the second derivative. So pick something less than 2, like 1. 2 minus 1, positive. 1 cubed, positive. Positive over a positive, positive. Now check the other side of 2, like 3. 2 minus 3, negative. 3 cubed, positive. Negative over a positive, negative. So it is concave up, and then it's concave down, meaning that 2 really is an inflection point. We now need to get y values for these special places. We found 2 special places, right? We found a local min and an inflection point. So the y values for those, remember y values come from the original function. So what is y at 1? All the way back to the original, it's 1 over 1 plus the log of 1, which is 1, isn't it? The log of 1 is 0, so you got 1 over 1 plus 0, which is 1. And what's y of 2, the inflection point? It's 1 over 2 plus the log of 2, which is nothing special. Okay? That's like 0.5 plus 0.7, so it's roughly 1.2. Okay? If you punch it into a calculator, you get something in the neighborhood of 1.2, I believe, when you try that. So I think we've pretty much got everything taken care of. We've got all the information in the charts. I haven't bothered to list out where it's increasing and decreasing, though it's pretty obvious, isn't it? The chart tells that story. I haven't bothered to list where it's concave up or down, but it's obvious from the chart. I haven't written out nicely the max is here, but we can see it's where it is. The max is at 1, 1. Actually, not max, min. The min is at 1, 1. And the inflection point is at 2, comma, this ugly mess, right? Now it's time to plot it. We've got all the information we're going to get. So we make our graph. And I'm going to favor the right-hand side because we're not allowed over there. That's out of the domain. We're not allowed to use negatives. Okay, and we know something happens at 1 and something happens at 2. And then vertically, I don't think we need to go much higher than 1, do we? Okay, we have a min at 1, 1. So the min is here, 1, 1. And we have an inflection point at 2 and 1.2. 1.2 is not that much higher than 1. So say about there. There's our inflection point. So there's our local min. Here's our inflection point. If we obey the chart and the asymptote, We know it's got to come down out of that asymptote. We know that as we go towards 0, where does it head? Positive infinity, so it needs to go up to infinity at the asymptote. It needs to be heading downhill out of it. It needs to be concave up. And so it must look something like this. As it passes through the min, it starts to head uphill again, but it remains concave up until it reaches 2. So I need this concavity to stay that way until I reach 2. Once I reach 2, what's going to happen? The concavity twists the other way again. Okay? So it's going to start concave the other way again at that point. Now, one thing we didn't bother calculating was the behavior as we headed towards plus infinity. But it's going to behave very much like the log function. Think about it. As you head towards infinity, what's this term going to do at the front? As you head for infinity, where is it heading? 0. So the bigger x gets, the less important this guy is. So that means for very large x's, what's this function pretty much like? The log. And we know the graph of log, it looks like that. So for big x's, our graph looks like this graph. In other words, it looks concave down, but heading slowly towards where? To positive infinity, which is kind of what the picture looks like over there. Does that make sense to everybody? Okay, there's half a class period gone on one problem. I won't ask if there are any more homework questions. We don't have time. Let's get started on section 4.7. Okay, 4.7. The topic is optimization. It's a word that you've probably heard before. Something is optimal means it's what? The best. It's the best for whatever you're doing, right? Something's optimal if it's the best it could be. Now, in most situations, something is optimal when it's the biggest it could be or the smallest it could be. It depends on what you're working with. If it was your corporation's profit, you'd want it to be optimal if it was the biggest. On the other hand, if it was your corporation's taxes, optimal might be smallest, right? If it was the strength of the bridge, you're an engineer designing one, optimal would be the strongest, not the weakest, right? That kind of thing. But optimization usually implies making something as big as possible or as small as possible. There are exceptions. Sometimes optimal is not best, is not biggest or smallest. It's always best. Optimal temperature in this room, not the hottest it could possibly be, or not the coldest it could possibly be, right? Optimal, it might even vary from one person to another what they consider optimal to be, but it's not going to be the hottest or the coldest. So there are situations where optimal isn't like that. But for our problems, they're pretty much all going to be make it as big or as small as possible. So there's a ton of different examples we could do that illustrate this idea. We only have time for a certain number. And we're going to start with it's usually the first problem in every calculus book that's been written. It's usually referred to as something like the farmer's field problem. I'm going to call it the rancher's corral problem. And it's an easy one to understand, which is why it's usually the first example. Most people can grasp it fairly quickly. All right, a rancher discovers 1,800 feet of unused fencing in the back of his huge barn. Now, this rancher has been meaning to build a corral, a rectangular corral to put his cattle in. So he decides to build a rectangular corral. Now, he's going to use this fencing he's just found. He wants this corral to be as big as possible. Okay? And he's got 1,800 feet of fencing with which to build it. Now, the rancher's smart, and he knows he can get a free side to his corral that doesn't require any fence. He can use the barn. Don't need to fence against the barn, do you? The barn itself is the fence. So he decides to build a rectangular corral against the barn. All right, now there was a reason I included the word huge here. The reason I'm including the word huge is I don't want you to for a moment worry about the barn not being long enough. It's huge, this barn. It's more than 1,800 feet long, this barn. It's massive. Don't consider the barn's length to be any kind of restrictive factor on what you're doing. Okay? So, the question is this. What dimensions would maximize the size of the corral? Okay, he wants to make it as big as he possibly can, but not spend any money. He's going to use this fencing he's found. Okay, so let's draw a picture. Here's the barn. For our intents and purposes, you could almost consider the barn to be infinitely long, okay? And we're going to build our rectangular corral up against it. So here is our corral built up against the barn. All right. Now, we want to know its dimensions, and there's lots of choices for those dimensions. There's an infinite number of choices for those dimensions that would always add up to the 1,800 feet. He could come out a foot, down 1,798 feet, and then back a foot. It'd have to be really skinny cows, right, to fit in there. But that's one ridiculous option that he could go with. Or he could go out 100 feet, down 1,600 feet, and back 100 feet, right? That's another option. And you can see how I could go on all day like that, making up choices. Our question is, by doing so, how could you make the corral as big as possible? Because they're not all equally sized dimensions in terms of the area they produce. That 1 by 1798 is probably one of the smaller ones, isn't it? So we don't know specifically what dimensions to use. What do we usually do in math when we don't have specific numbers in mind? Variables. X, Y, and another X. Does that make sense? And what can we say about the X's and Y's based on how much fence we have? They add up to 1,800. Yeah, that's called a restraint or a constraint on the problem. So we have a constraint, and the constraint is that 2 X's plus a Y have to add up to 1,800. Does that make sense? 2 X's plus 1 Y add up to 1,800 feet. Okay. That is not the thing we're trying to maximize. That's just the fence. That's how long the fence is. It's just a fact we must obey. But what is it we're trying to maximize? The area. Area is easy. It's a rectangle. What's its area? Length times width. And what have we tagged those as? X and Y. So the area is X times Y. Is that right? So we need to maximize the area, which is X times Y. Okay, now we have a problem with that. Normally maximizing functions, we know what the job is. You take the derivative of it, you find the critical values, you test those critical values to make sure they're what you want maxes in this case, right? But what's the trouble with taking our derivative right now? We've got a Y in it, we've got too many variables. And no, we're not going to do it implicitly or anything like that. We would like to lose one of these variables. Now, how could we do that? Solve for Y where? You're right, solve for Y in the equation above, in the constraint. We know we've got to obey this constraint, but it also gives us the opportunity to find a formula for y in terms of x. We can easily take the 2x to the other side and write this as y equals 1800 minus 2x. And that means anywhere I see a y, I can replace it by 1800 minus 2x in this problem, because they're the same thing. And that's just coming from the constraint. So now we get that the area is x multiplied by 1800 minus 2x, or if I multiply that out, it's 1800x minus 2x squared. This makes sense so far? So that's the area. That's the thing we're trying to maximize. We want to make it as big as possible. Now, we do now want to figure out, is there a domain restriction on x? Is there some sort of set of values that x has got to stay between? Well, there's one really obvious restriction. It can't be what? It can't be negative. Yeah, x has got to be a positive number. You can't have a negative width corral. It doesn't make any sense. So x has got to be greater than or equal to 0. It literally could equal 0, although that would be pretty silly. You come out, no feet. You take the fence 1,800 feet along and you lean it against the barn, apparently. But I guess it's theoretically possible. You could do that. You couldn't make it negative, but you could make it 0. So that's the low end on our domain. X has to be greater than or equal to 0. And what's the high end of the domain? What's the biggest x could possibly be? Think about this is what we call a physical domain. It's not coming from the formula. The formula, it says x can be absolutely anything, doesn't it? We're not getting any restriction here. It's a little parabola. Parabolas don't care what you plug into them. So no restriction there. The restriction has to come from the physical problem. What's the biggest x you could possibly use here? Don't forget there's 2 of them. It's 900 feet. And it would correspond to making y be 0. You'd go out 900 feet, wrap around a fence post, come straight back. Is that right? But it's possible. Stupid, but possible. So that's the upper end of our domain. X has to be between 0 and 900. And now we want to maximize that function on that domain. And we have 3 techniques we can use to do it. All of them start the same way. It's how we finish them that could be different. Where's the max going to lie at? Well, it's a continuous function, because it's just a polynomial, and it's on a closed interval. We have a little theorem about that. It's called the extreme value theorem. And it says, where does the global extrema of a continuous function on a closed interval have to lie at?
Either end of the interval.
Either end of the interval, yes.
Or C, like a value in between.
Or a value in between that is a what? This is a critical value in between. Yeah, that's one technique we could use. Another technique we could use is we could just find the critical value and test it with the first derivative test to make sure it's the max we're after. Or, alternatively, test it with the, what's the other derivative test? The second derivative test to make sure it's the max we're after. So those are our 3 ways of finishing the job. Okay? But all 3 of them require that we know the critical value. So what's the first job? Get the derivative. Okay, let's find the derivative. What's a prime here? 1800 minus 4x, is that right? Okay, critical values are going to be places where this derivative is 0. Undefined is off the table, isn't it here? The undefined kind of critical value. Why? It's a polynomial. They're never undefined. So we only have to worry about a prime being 0. So that gives us 1800 minus 4x is 0. Okay, now we want to isolate the x. So 1800 equals 4x. So 1800 divided by 4, which is 450. That's x. And that's the one and only critical value we have here. That's almost certainly what we're looking for. But it does need verification. Now, as I said, there's 3 methods you could do to finish this. Now let's go over the list again. You could use the extreme value theorem, where we would take the 2 endpoints, 0 and 900, and the 450, and plug them all into the area formula. And whichever one gives the biggest answer has to be the absolute max. I'm pretty sure 450 is going to be the one that does it, because if you think about it, if you plug 900 in there, that's 0. And if you plug 0 in there, the whole thing's 0. So it's bound to be the 450 that does it. So that's one way. The next way is the first derivative test. We could make a chart, mark 450, check both sides, show that it's going uphill on one side and downhill on the other. That means it's a max. Or we could use the second derivative test. And in optimization problems, we almost always use the second derivative test because it's usually the quickest. It's not universal, but I'd say at least 95% of the time you tend to use this last one I'm mentioning, the second derivative test. And let's use it here. The second derivative test. And to use it, we will need to know the second derivative, which in this case is trivially easy. What's the second derivative? -4. Now remember, the second derivative test says you plug into the second derivative your critical value, which is 450. So I'm supposed to take the function a double prime and plug into it 450. Now the thing is, a double prime here is so trivial, it doesn't even have an x anymore. If it had an x, what would I do? I'd put the 450 where the x is. This is so basic, it doesn't even have an x. It doesn't care what you plug in. It always spits what answer back at you? -4, no matter what you plug into it. It's kind of obvious that would be true. This is an upside down parabola, isn't it? Permanently concave down. So no surprise that it doesn't change its concavity. Okay, so this is negative. That means it's concave down. That means that what we're looking at must be a what? A max. So we found our max. 450 feet. X must be 450. The question said, what dimensions plural? Okay, we found X. What do we also need to find to answer their question? Yeah, we need the Y as well. Okay, so how do you find the Y? The Y value? We've got a formula glaring at us up here in red, don't we? What's Y? 1800 minus 2x. So the Y is 1800 minus 2 times 450 in this case, isn't it? We know that x is 450. Okay, which is 900, isn't it? Okay. All right, so final answer, what are the dimensions that they should build this corral? The dimensions should be 450 feet by 900 feet. That will make you the biggest possible corral you can build against your barn with 1,800 feet of fencing. Those dimensions there. If you want the actual area, you can multiply that out on a calculator or something to get an answer. We weren't asked what the area was, just what the dimensions were. You also might want to get a little bit more detailed, just in case your ranch hands who you set to work with those instructions are a little bit dim. Because if you're not more specific, your dumb ranch hand might do this. 900 feet, 450 feet, 450 feet, and the guy says, boy, the boss likes big gates. Right? So what had you better tell them here? Because this is not what you had in mind, is it? That the 900-foot side is the side that runs parallel to the barn. Okay, that's parallel to the barn. So it's clear what you mean by the 450 by the 900. Are there any questions about that? Okay, we've got about 7 minutes left. These take a lot longer than 7 minutes, so let me just kind of give you an overview of the kind of things we're going to be looking at. Optimization problems come in lots and lots of different flavors. One of the problems we're going to look at next time, we're going to look at why tin cans are the size they are. Have you ever noticed they're all pretty much the same shape? They're all cylindrical, but it's kind of, you don't see too many tin cans that look like this, do you? Right? And you don't see too many tin cans, unless it's a canned pizza, that look like that either. Tin cans pretty much tend to look like this, don't they? They're all cylinders, but why go with that shape cylinder as opposed to that shape or that shape? It's optimal in terms of the amount of metal. You assume that they're all built to hold the same volume. You know, I need a 1 liter can. I could make it that shape, or that shape, but I'm going with that shape. Why? Because it uses the least material. It uses the least metal. We're going to do that problem and show why it's the shape it is. Some of the other things we're going to look at problems involving optimal decisions for pricing things so that you get the most profit by the price you set it at. Most of you are pretty much aware of this, even if you've not had a class in finance or business. What's the control that a business has over the number of sales they make? What's their most easy way to control the number of sales? How can you make sure you sell more of your thing? Make it cheaper. I mean, you can advertise and all that stuff, but the most easy way to get more sales is to lower the price. Okay? The trouble is, you sell more of them, but what happens to the profit you make on each of them? It gets less. So it's kind of a balancing act you have to play between upping or lowering the price and hence upping the volume or the number of sales you make on your bottom line. If you drop the price too far, you may be making tens of thousands of sales, but you're selling them for so little, you may even be making a loss. So what tends to happen with that sort of scenario is, depending on the price you charge, you get graphs that look like this for your profit. Here you're selling them for nothing, right? Here you're selling them for a lot more, but the overall profit arcs up at first and then heads down again. So where do you want to price them at? If this is your price and this is your big P profit, you want to price them this much. So you hit that sweet spot on the profit that puts you at the peak there. We'll look at problems like that as well. Okay. We'll look at other problems like designing various objects so that they're their optimal shape. Kind of like Corral, only 3-dimensional problems. We'll look at that as well. Lots and lots of optimization options. It's all about balancing two things that kind of are tugging in opposite directions. Here it was pretty obvious. X and Y were pulling in opposite directions, right? The bigger you made X, the smaller you had to make Y. That tends to happen in most optimization problems. You've got two things. They're not necessarily 2 dimensions, but two different things that tug opposite ways. In the pricing problem, the bigger the price, the smaller the price, the more you sell, but the less money you make per item. So you've got two things pulling in opposite directions. And it's striking that balance between these opposing forces that tends to get you what you're looking for. So lots and lots more of these examples coming up. Most of the rest of the week we'll be doing optimization. Lots and lots of these. And most of you have noticed that we're ahead of schedule. I don't think we'll be ahead of schedule by the time we finish optimization. They are long problems. And you need to see as many of them as possible, because you don't know what you're going to see on the exam. The one thing I'll tell you, the one you see on the exam won't be any of the examples I did in class. That's the whole point. You're supposed to be learning a technique, not, oh, I've memorized how to do the tin can problem. Now let me show you how I can do it over again on your exam. It's supposed to be, oh, here's a brand new problem. I can do it because I've seen so many different types of problems. So I want to give you lots of variety. All right, that's it for today.